So let's start. So when you hear about like what we're going to do today, this is the content. So our focus mainly is going to be on the load cell modules. We see the introduction, how to install, how to wire the load cell module, and then the functions that we have in the load cell module, and also the control register, the mapping. And lastly, we'll see how to calibrate the load cell module to measure the right weight for your application. So let's go to the introduction. So like the load cell module we are looking at today belongs to AS series PLC. So we have different brand of PLC, but the module we are using today belongs to AS series PLC. So you can use the load cell module on AS200 or AS300 PLC. The AS300 PLC, as you could see, has different peripherals. And one of those peripherals is the I/O modules. So you can attach digital I/O modules to it. And then you can also attach analog I/O module to it. But today, the modules we have that we're going to attach to it is the load cell module. Sorry, the load cell module. So the load cell module is basically an analog to digital converter. It takes the output from your load sensor and it converts it to a digital value. And based on that digital value, you can control your machine, you can do what you want to do. So this, our focus today, the load cell module is an analog modules that you can use with AS200 PLC or AS300 PLC. So when you talk about a load cell, or as I mentioned, load cell module, the first thing that will come to your heart is load cell. So what are load cell? Load cell, they are also called load sensor. So they are devices, they are sensors, they are designed to sense force or weight. So for example, this is an example, is the one I have here. If this is a load cell, you can also call it a load sensor. If you apply a load on this load cell, there is the output terminal. This one is the white cable, the green cable. It will output a voltage that is proportional to the force you have applied. So if you had little weight, the voltage that will be output that will be outputted from here will be not so big. And if you had the maximum weight that this module can measure, you are going to have the maximum output voltage that corresponds to the weight that is being applied to it. And for this to work efficiently, the load cell has sort of, this is the internal configuration. It receives what we call the excitation voltage. So this is the plus, this is the minus. So the load cell module, like we saw in the first page, supply this excitation voltage to the load cell. So what happens is that this is the strain gauge, the cell itself. This is the internal configuration of this device. So if a force is applied here, which is also here, there will be an electrical resistance. So there will be a signal corresponding to the applied force. So that force you have applied will generate a very small voltage, millivolts, corresponding to the force applied. And then there's an internal circuitry in the cell. So this internal circuitry, if it receives 5 volts from the load cell module, it will amplify the small signal to a bigger voltage that will be read at the output. So this output is what the load cell module of AS PLC takes. Then it converts it to a digital value. And based on that digital value, you can now control your machine. So this is just the picture representation of how this load cell works. It's a gauge, it's a strain. If you apply mechanical force on it, there will be a change in the resistance. So that change in the resistance will produce an electrical signal, millivolts. It's very small voltage. And then there's some form of an amplification circuit. In this case, is with some bridge. So this circuit amplifies the small voltage, and then it gives you an output voltage that corresponds to the mechanical force you have applied. And this output voltage varies from sensor to sensor. And the output voltage depends on the eigenvalue of the sensor. So each sensor or each load cell, they have different eigenvalue. So the eigenvalue determines the characteristic output of the sensor. That's why if you are configuring your load application, you need to choose the eigenvalue that is compatible with the sensor you are using. The sensor I showed you earlier, it has an eigenvalue of 1 millivolts. So if you are configuring the sensor in the load cell software, as we will see later, you have to select one. Then if you select one, which is the correct eigenvalue for that load cell, then it's going to measure the correct weight for your application. So basically, these are the load cell or the load sensor operates. And then here is where we get the data into the load cell module. So the load cell module of AS300, you cannot calibrate this output to what you want it to be. So you can really manipulate the readouts from the sensor. And then that calibration, you can use it for your application to make your weight application very efficient. So this is what happens. It goes to the load cell module. And then the load cell module has an analog to digital converter. With that digital converter, you calibrate that very signal. What comes in here is analog signal. So you calibrate it to give you a very smooth digital value. And that digital value you use to operate your machine. And then if we think of the applications where load cells are being used, it's so numerous. In summary, any place where you are going to load is needful, then a load cell sensor is useful. A load cell is needful. So some of them, there are very many, depends on your application need. Some of them could be dual tank level control, food packaging. If you are packaging the food, you want to know the weight. So as you are filling up, the sensor is reading the weight, is giving a digital value in the load cell module, and the PLC can see. So when the digital value of your interest is reached, you can trigger any action in the PLC, and the food packaging maybe stop packaging the food it was packaging. Another possible application is bag filling machine. Maybe it's a bag has to have a certain weight. So you can use a load cell module for us. We don't have load cell sensors, Delta. You can use anyone on the market, but we set the load cell module. Then you can connect the sensor to the module to make your application. So when the bag has reached the level, the weight specified, you can trigger some algorithms in the PLC, and then the action will be triggered. You also have bottle filling application. You need to measure what has been filled into the bottle. Packaging machines, you can use a load cell there. Inventory control system, maybe different goods are coming in. You want to do sorting. If this is 5 kg, move to the right. If this is 3 kg, move to the left. So you are controlling the inventory, the stock that is coming in, maybe to the storage house. You can use the load cell there. Printing machines. So any application that needs weight, where you need to measure weight, where weight is very sensitive, then the load cell is very handy. You can use it there. Let's look at the installation. It's quite very easy to install. I have one here. I will just show it to you. I will switch my video and show you this one to you. So to install it is very easy. Vertical installation. You just need to take it out and put it in. So if it's broken, you can easily replace it. So it's very easy to install. So once you install it to the right-hand side of the PLC, then the PLC knows that, okay, the load cell module is at this position. When it comes to the time of address mapping, the PLC, the CPU will map the corresponding address to the load cell module that you have added to it. I will just show you, okay, during the time of when I'm showing us the wiring session, I will just show you the configuration that I have here. So let's proceed. This is the wiring. So to wire the load cell to a load cell module is very easy. What happens is that when you buy a load sensor, depends on the name you call it, the cables on those load cell is being labeled. So each cable corresponds to a signal. Like this very load cell here, it has red cable. The red cable is the positive voltage, excitation voltage. This is the voltage that the load cell module supplies to the load sensor. This is the red, and the black is the ground. So you connect the red to the red and the black to the black. And then you also have the green and the white. So like here now it specifies. So if you look at the data sheet of your load cell module, of your load cell or load sensor, you will see the cable indication. Then the signal plus to this signal plus, the signal plus and the signal minus, which is white, in this case, to white as well. So this signal terminal, this is where the load that the sensor measures, this is where it gives it to the load cell module. And then on the load cell terminal, load cell module terminal, AS, you have the sense plus and sense minus. So this terminal is there to compensate for impedance. So in case you have the sensor installed in a very far distance, so if this is connected, it will ensure that what is being read from the sensor is correct. So it will help to balance the impedance so that there's no issue, there's no interference, there's no error in the reading. So you connect this to also the excitation voltage as well. For the 4 cables, you do the same. And also there's also 6 cable configuration. There are some load cell or load sensor, they have 6 wires. So this is how you also make the connection. It's basically like the 4-wire type. It's just that this has 6 wires, and then the connection is more or less the same. Another thing that the maker puts some specification. Like this one I have here, you see some specification. This is the capacity. The capacity I have is 5 kg, and there is something that is very important is the rated output. So we call this gain value. It's very important. I will switch to the video camera of my settings while my voice recovers, then I come back to talking. So I will switch my video now to HD, and then I put this for you to see. The measurement, the setup that I have. Let me switch the video to the other video camera. You can see here, this is the setup I have here. You can see this is the CPU. And this is my load cell module. We can see a lot of wire. If you can see carefully, you see some cable with long. If you can spotlight the video, to be very good so that they can see it big. Just a moment. You spotlight it. I think I can spotlight it. Let me see. Spotlight for everyone. Okay. Yeah. Okay, now you can see very well. So this is the setup. You see, I have the connection, the signal cable is connected, the excitation voltage is connected, and then you see this is the load cell that I have is 5 kg. That's what you can see on the PowerPoint. The specification is also there. So the gain value of this is, if you can see my screen, the gain value of this is 1 millivolt. It means that when the sensor is outputting 1 millivolt, the maximum voltage of 5 kg is being measured. So this is the setup. So what I'm trying to show you is that it's very easy to set up. Just follow the wiring guide, and then you have it ready. So we'll proceed. I will switch the camera now, then we can proceed. So what I was saying before I was interrupted was that each sensor, they have what you call a specification. One of the specifications that is very, very, very important, that's very, 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 very critical, is the Einge value, the rated output. So the rated outputs determine what the sensor measures. For this, in this case, is 1 millivolts for 5 kg. So, and each sensor have different Einge value that has been specified. So what happens is that in load cell wizard, if you are configuring this load cell for your application, for the software, you need to select a Einge value, sorry. You need to select a Einge value of 1 millivolt, and then you are done. Your settings will be correct. So let's proceed. So then let's look at the specification of the load cell module. There are quite some specification in the load cell module that is very important. For this load cell module, the model name is AS 2-channel load cell. Then the power supply is 24 volts, like I showed you what I already have there. And then the analog to digital converter, the resolution is 24 bits, so it's very sharp conversion. And the excitation voltage, what happens is that the load cell module supplies the sensor the excitation voltage for the sensor to amplify the small voltage it has to a voltage that can be read to have the correct reading of the weight that's being measured. And then this is what I told you is very important, the Einge value. So for each load cell or load sensor, the manufacturer has specified what is the Einge value. It means at the specified Einge value, this would be the readouts that will be in the strain gauge of the internal sensor. And then we also have different type of sensor, 4-wire or 6-wire load cell or load sensor. And also the maximum distance that you can install the sensor far away from the module is 100 meters. See, it's quite big. It's like the length of a building. And then the precision. So the precision is also very important. The precision of this load cell module is 0.04. You multiply this with the Einge value with the excitation voltage to see how accurate the reading that the load cell module is reading, how accurate it is. And then you also have the response time. So this response time is the time it takes the load cell module to read the weight, the load signal, the weight signal that is coming from the load sensor. So let's how will I say, let's bridge this to selecting a load sensor. Looking at this, if you want to select a load sensor, so how is this applicable to that? The exciting voltage. So for our load cell module, ASO2LCA, the excitation voltage is 5 volts. So if you want to use a load cell, a load sensor on this module, you need to choose a load cell that supports 5 volt DC and above. 5 volt DC and above. So if you have a sensor that require more than this, it means that you cannot use this module. If you have a sensor that also require lower more than this, it means you cannot also use it, because this is the excitation voltage is supplied to the load cell. Another thing that's also important again to select a sensor is the Einge value. So this determines the characteristic output of the sensor. So for us, for this module, these are the Einge value that is being supported from 0 up to 80. So for example, if you have a very gigantic load cell or load sensor that is more than 80 millivolts, it means you can't use this module, this device, because the Einge value cannot meet up to the requirement. And do you know what will happen to that? If you use it, what you are going to read the reading will be wrong. So that's why this iron gate value is very important. So we have a question. Yes, that's a good question. Yes, Shami. Yes, you can connect two load set to one channel in order to get an average weight value. Yes, it's possible. So you connect them together, then you connect it to one channel. And then what is being measured is averaged. The advantage of that, it helps you to have a balanced reading, a reading that is not distorted if you combine two together. So it's possible. You can do that. You can do that for 4-wire type of load cell, for 6-wire type of load cell. It's possible. So that is for this. So for us, for data module, the maximum iron gain value we support is 80 millivolts, from 0 to 80 millivolts. For example, if you have a sensor that supports 100 millivolts, then you cannot use this. If you use it, the reading will not be accurate. So that's the iron gain value. It also helps you to select the correct sensor. Another factor again to select a sensor is the maximum rated load. So it's good that if you are selecting a sensor, you choose a sensor that is close to the maximum load you are going to measure. For example, you want to measure maximum 10 kg. So your application, your machine is maximum 10 kg. So it's good you choose 10 kg load cell, 10 kg load sensor. If you go and choose 50 kg, so there's a big gap. So you will not really have, the accuracy will not be so perfect as much when you choose a load cell that has a maximum rated load close to the load of your application. Another factor again, when you are selecting a load cell or a load sensor, is the wire configuration. So for 4-wire, you can, for short distance, 4-wire configuration is very good. But if your machine is far and you want to, this load sensor is far away, up to like 100 meters, then it's advisable to take 6-wire load sensor. Then this 6-wire load sensor will compensate for the impedance that will be created as a result of the long distance. And then you also have the precision. You have precision. So for us, the precision is very high. If you multiply this with the iron gain value and with the association voltage, you have an indication of how precise your measurement will be. So different load cell module. For this, we have 0.04% for different modules, not for data, maybe other brand. The precision could differ. Another thing that's also important again is the measuring time. So the measuring time also, I would like to say, closely related to the precision. So when you are measuring your application, it is good, if possible, to choose a bigger response time. So this response time is the time it will take for the load cell module to sample the signal, the analog signal coming from the sensor. So when the time is big, it makes what is being measured to be balanced. So the bigger the time, the more stable the measurement and less interference you will have in the measurement. Okay, that's for that. Then how do we program the load cell module? I think I see one of our colleagues on the call, Shami, you already have experience with the load cell module. Maybe some of us here, this is your first time with the load cell module. So what are the options you have to program this device, to configure this device? One of the options is DI Designer. So in DI Designer, there's an integrated load cell wizard, LC wizard. If you start on that LC wizard, there you can configure, you set the parameter of the load cell, of the load cell module, in compatibility with the specification of your load sensor. So you set it up in the load cell wizard. One of the advantages of this is that if you do this in the load cell wizard, if you download it to the module, your configuration will be retained. It means that if you power off, you lose power, what you have configured will remain, it will not change. That is one of the possibilities you can use to configure the load cell module. Another possibility is to use what we call API, an instruction. From is to read from the load cell module. You know, when you measure this load cell module, see it together with the sensor, because everything coming from the load sensor is already here. And from this guy, you can take everything that is coming from the sensor, because the sensor reports to him, and then this reports to your application and everything that you need to do. So you use the tow command to write parameters to the module. Another one thing that is important to note here is that if you use tow instruction to write, what you have written will not be retained. It will not be retained. So if you lose power, or there's an accidental power off, what you have configured will be lost. So when you start up the PLC and you trigger the application again, then this instruction can rewrite back those parameters to the module. So these are basically the two ways you configure this module. And also, besides tow instruction, it's also possible there are some specific address, special address, important address you can also write in the DI designer. So if you open monitor table, you set up the address, you can also write in some parameter to it. If you look at this side, you can see some parameters or control registers that is very important in the load cell module. Channel 1, 0 for channel 1, the control register is 0 for channel 2. If you look at this module, there's two channels. Up is channel 1 and below is channel 2. So each of the channels, they have their specific control register. So this control register, you can command them read write using this instruction. Using instruction. You see the endgame value also for each channel. So depending on the sensor you have chosen, the specification of your sensor, yeah, you choose a correct endgame value. So you can use this API to tell the module for the sensor you are measuring, this is the endgame value. And then you can reconcile that with the signal that is coming from the load sensor. That's for that. Then you also have this sampling cycle. So it's also very important. For this, the control register is 2 for channel 1, and for channel 2, the control register is 61. So you can set different time. I think the maximum time that we saw in the other page is 400 milliseconds. So the bigger the time, the more stable your measurement is likely to be. Then you also have registers you use for calibration. So the essence of calibration is to have a very precise digital value that is proportional to the analog signal coming from your load cell or from your load sensor. So you can use this calibration function, look at the registers, you can write to them, and then you can calibrate the load cell modules. Then it knows that, okay, if I read these millivolts from the sensor, this is the digital value that I should give to, that should be available for programming. And just as you can write to these registers with this API, in the load cell wizard, it's also possible to access this function if you use the load cell wizard. But this is more robust because what this can access, the load cell does not have access to it. So the load cell wizard have access to very important registers. With the load cell wizard, you can configure the endgame value. With the load cell wizard, you can configure the sampling time and some very sensitive parameters. But other parameters, you don't have possibility to, you don't have access to it from the load cell wizard. Then you can choose this instruction to read or write from those very parameters. So this is calibration point. This is the calibration weight, the weight you calibrate. So it's okay for this point. If I measure this also weight, this should be the digital value. And then if we proceed further, you'll see that then there's also another register is register 200. This register is both for channel 1 and for channel 2. What this register does, it's a state register. It gives an indication of what is happening in the module. So normally it gives when there's an error, some bits from bit 0 to bit 15 could turn on, indicating, oh, in this very bit, there is an error. And you can reconcile that error to what is happening in the module, because each bit has a meaning. I think I have it later on. You see it I think at the end of the presentation. And then you also have this command set. So this command set is where you trigger some command. So there are some numbers you write to it. That number has a meaning. Once the module receives that number, for example, number 9898, it means start calibration. If you write that to this register, the module will start calibrating this input signal that is coming to it. So this register is called command set. So some of these registers, they are very useful in your application. Yes, I think I will just share my screen again and demonstrate this on the GR Designer itself. So what happens here is just the control register mapping. So when you start up your application of load cell, there are some special registers that the CPU assigned to your to this module. Let me share my screen again, and then we can just see. So I suppose you can see my screen now. Then this is my DR designer. I suppose, yeah, it's possible now you can see the DR designer. Okay. So the CPU that I have is AS200, the analog type. Let me check if my connection is connected. So we have COM manager. There's a communication driver we have. I think if you're not familiar with Delta PLC, with that communication driver, you connect this software to the PLC, and then you can configure which parameter you want to configure. So now my cable is connected from the CPU, this CPU, to my PC. Let me try to connect. Yes, I'm connected. So you can see, let me hide this panel. I think you are seeing this also. Let me hide everything you are seeing now, so that you can have a clear view of what we are doing. Also this, break it down. So now you see I'm connected. So to configure this PLC or any module attached to it, if I expand this, close, I come to configuration. So I already have a load cell module attached to it. Let me delete it. If I delete what I have here, I want to scan again. If I scan, you should see it probably. Then if it sees it, it fills it up itself. It's two ways. Either you add, if you double click, yeah, analog, load cell module is an analog. Look at the load cell module. If you add it, okay, you see it's added, but I don't need this. Let me delete it. So now I have my load cell module added. What I was saying is that if you click on the CPU, you see this CPU it already mapped some address to these load cell modules. If you click on this tab, you see detailed information of the address that is assigned to it. So see, I've opened it. This is the address assigned to it. The first one is error code from 228,000 to is double word, is error code. And then you see the inputs for channel 1 and also for channel 2. These are the address assigned to it. This was what I told you, command. It's like this D0. This D0 is the command address. So there are some various commands you can write to it. This is what I mean. If I show you this, I think this is the manual for the, it's somewhere here. Yes, this is the status code. I think I showed that earlier. Is up. So this status code is a 16-bit register. So when there's error on the load cell module, it gives you an indication of what the error could be. Bit 0, it means that power supply, there's issue with power supply, like bit 14, bit 12. So each bit has a meaning. So this status code, that is what you have here, status code. So the software mapped DCs to the status code. So anything you see here, if I go online, indicate what that bit stands for, plus other error code. And the software itself, the CPU, also automatically map D0 to the command register. If I go back to where so this is the bit status code. The one I was telling you is 201, is done here. Yeah, this is command set. Command set. So this register, control register 201. So if you want to use to and from instruction to configure the module, you write it to this address. But in the case of our software already just assigned D0. So anything I write in D0, it's like data exchange. It goes automatically to this register. So let's go back. So you see there are different commands like 98. That's what I meant. If you write 98, it means you want to this register, it means you want to start calibration. If you write 99, you want to deactivate calibration. So there are different commands. There are very many that you can write. So depending on what you want to do, you write a command to this register, and then the module starts behaving according to the command that you have written. So you can download this manual. It's AS PLC module manual. It's also on the download center that I showed to us earlier. Let's go back to the software. So this address is already mapped to it. Can I let me go online? Okay, I have not downloaded. Let me download the configuration I have. So we have downloaded the configuration I have. So let's go back to our presentation to know, so that we don't miss steps. So if I go online now, you can see the current value that is in these addresses, and this is what each address represents. Okay, before we go to the function, let's just play around with a little bit of the interface I showed to us earlier. So if you want to configure the module, it's two things. Like I told you, to instruction. If you come to programming, for example, if you write to here, you see this is to instruction. So if the operand of this to instruction is here, you specify the address you want to write to, the address in the module you want to write to, you write it, then the data you are sending, this is data you are sending, goes directly to the address control register that you're writing to. I think, let me see. Sometimes if you press F1, it also F1 key, F1 on your PC, it opens up the F menu of this module. Yes. So it tells you what is the operand and what each stands for. like if you go down, it defines it. See, M1 is the module of the remote extension module, and you have M2, the order number of the extension module. You have M3, the control register. So for example, if I want to write command, I need to make it 201 because the control register I want to write to is 201. A device in which the data is stored. So where am I storing the data? I'll specify it here, and then the device in which the error code is stored. So it's very easy to use. What I'm trying to show you is that if you want to configure that module, this is very handy to configure it. So I think let me remove it so that if we want to download, we don't have issues with downloading. And then that was the first way, the instruction. There's also another instruction from, it's similar to that one. If I click here, I just write from, F-R-O-M, enter. So it posts it there. So what this does, this reads from the module. Maybe you need to read the measurement, you need to read some value. You use this instruction to read, and then you have the value that is in the module that is coming from this sensor, the weight sensor that is measuring some measurements in your application. To and from. And then if you go back to, I already opened it before, the configuration itself. So if you double click on this, I'm using GI Designer. So GI Designer is one of our GI Studio software. You can use this software, GI Designer, to program our server drive, our HMI, no, not our server drive, our inverter, our PLC, and other devices. So it's one software, and this same software, you also use it to configure the load cell module. So in the past, we have software for every product. You cannot, our software was countless, but now we have one software compact for almost all the control products that you have. You can use this software, GI Designer, to configure those devices. Another one, again, I'll touch on it later. If you double click on this, it opens up the load cell wizard for you. So from this load cell wizard, you can configure what the control register does. That is what this load cell wizard also does. If I go online, so you can see there is no value because I've not even configured the module. But we'll soon get there. When I configure it, you see that if I apply some load on my sensor, it can read some value, suppose. Okay, yeah. You can see some value already. This is just like raw data from the sensor. So then later on, before we bring this meeting to a close, we'll look shortly on calibration. So the essence of calibration is to make what you measure to have a correct digital value. So digital value are the values you have in those registers I showed to you. So and based on that digital value, you can now rehearse in your application. So now let's go back to our presentation. So basically, this is where you set up the basic setup of the load cell, module, and then you are ready to program your machine. Then the digital value you have, you can tell your machine, if I read 1000, do this. If I read 2000, execute this command. It's just as simple as other PLC or program algorithms that you implement. Then I close the load cell module. Let me also go online. If you see in the program, in the monitor table, I have some monitor, some addresses. That was the address that was here. So if you come to this place where I was, if I click on this for the load cell module, you see that this address was automatically assigned by the CPU, the PLC, to the load cell module. So input channel 1, the input, the value that is being read is from 28002. So it assigned this automatically. You can see what it assigned is so limited, and we have up to like 100 parameters in this module you can read, write, with, to, and from. But the assignment by the CPU does not cover all those multiple registers. But with to and fro instruction, you can get access to all those control registers and do what you want to do with it, especially if you have a system that you want a very high precision, then you can use that to command it. Let's go online. Let's see which value do we have. So what I did is that I set up a monitor table and I put these addresses there. So let's go to the table. What do we have on this table? I go online, compile and download. The program is not compiled. Switch to online mode without downloading. So you can see the input was 2802. You can see, I'll just touch my wiring. So you can see that I'm getting some signal from the load cell, from the sensor. I think where we saw in that register was 202. So this one, 202, yes, 202 is the input coming from the sensor. So now let's go to our presentation, then we'll come up to wrap up with some short configuration. If I come to our presentation, that's it. No, it's not. So now what we're going to look at now, we're going to look at some functions in the PLC. So this is what I was showing to you. The address is mapped. And another thing on this very address, for example, this command, you can see command here is D. Anything you write on D, automatically it goes to the command register. It's executed. So it's the same thing that the to instruction would also do. So now let's wrap up this section with some of the function of this load cell module. So what can you achieve in your application if you decide to use this load cell module? One of them is measuring weight, the net weight. So with this load cell module, two-channel AS02LC, you can measure the weight and you can get those values in this control register. Control register 0, control register 60 for channel 2, for channel 1. So in this register, you specify which weight you are measuring. You can measure the tail weight, you can measure the net weight, you can measure the gross weight. So there are some applications where you are sensitive to this type of weight. For example, maybe you have an empty bucket. The bucket has to be filled up, and you want to measure what is being filled into the bucket. So you need to know the tail weight. What is the tail weight? The tail weight is the weight of a package. So in the case of the bucket, the tail weight is the weight of the bucket. So you can get the tail weight value in this register. So you see, it's very easy and handy to control your load cell, the weight you are measuring using this load cell module, because you have access to each data in a specific register. Like this register is a double word 32-bit register. You can see the tail weight. And another thing that's also very interesting is that you can set a tail weight. You can set a digital value that if this module gives you, if you read this digital value from the sensor, this digital value is my tail weight. So it means the weight of a package. It's when there is no load on the load sensor, the weight of the empty bucket. Another weight again is the net weight. So the net weight is the weight of the product. Here you can get the net weight of what should be measured. Channel 1 is double word. Channel 1 is 6. Channel 2 is 65. And then the last weight is the gross weight. So the gross weight is addition. In your application, you may want to know both weights before you take action, before you write your instruction, your algorithm. So you get also the gross weight from this register. So this is the first function. You can measure your weight and you can be so specific on the type of weight that you want. Is it tail weight? Is it net weight? Is it gross weight? Another function is stability check. So stability, once you have set up the module, I want to check if your measurement is stable. There are some flags. I showed you this register before, control register 200. There are some flags there you can monitor to see if what is coming from the sensor, what is being read is stable. And how does that happen? What happens is that in the control register for channel 1, control register 4, you specify what is the range of the value of the weight you want to measure. So when we talk about the weight, there is an analog value coming from the sensor. There's a digital value corresponding to that analog value in the load cell module. So the load cell module only gives you digital value 1, 2, 3, 4, 5, 6, 7, 8. But the load cell or the sensor itself gives you voltage. So the load cell module, gives you the equivalent of that voltage in digital format. Maybe 1 kg is equal to 1,000. 2 kg is equal to 2,000. So what happens here in the stability check, you can specify which range of measurement you want to take as, if I'm reading this value, it means my measurement is stable. So if you set that up in channel 1 with this register, or you set that up in channel 2 with this register, what happens is that when the measurement from the sensor, what is being read, or the digital value in the load cell module is in this range, there's a control bit 15 and bit 14. Bit 14 for channel 1, that bit will be high. So it's like a flag. So if you see that bit, you can read it with 2 instructions. If you see that bit, it means that, what I'm reading is still balanced. And in the case of our configuration, if I switch to our program, if you see, I think it was, if you come to hardware configuration, if you go to that place again, the status is state code. Here is this. So this is a 16-bit register. Bit 14, if bit 14 is high, for example, it means that channel 1 measurement is in the steady level, is stable. And besides this, I also showed to you that there's a control register 200. So what this have, you can also see it in control register 200. I think I'm here. Yes, good. This is command set. If you don't use this, because this is being mapped by the CPU, you can use to and fro to get this control register 200. And that, you see, bit 14, the weight measured by channel 1 is in the stability range specified. So it could be your application is very, sensitive. You want to monitor every step of the weight that is being measured. And then if this bit is on, it means that everything is okay. Then if we go back to our presentation, on the other hand, if the range, you see now the range has exceeded, it is just going to, it's like overshooting, and then the bit goes low. So bit 14 for channel 1 is low. So it means that what is being measured now is not stable. It's out of the range you have specified on this register that you take as a stable range for your machine. Stability check, that is the second function. Another function again is determining 0 point. So it's possible you want to determine 0 point. Well, how does that work? If you put no object, or if you remove an object from the this is load cell. If you remove an object from the weight, from weight, and there's no load, you can get an indication. This is also control register 200 or D6, like we saw there. And mind you, D6 could be different. Maybe your PLC, your CPU map a different address. But in my case, the CPU map D6 to this 200. So what you have in D6, you have it in 200. So they are mapped together. So what happens is that if you remove, if there's no load for channel 1, bit 12 will be triggered. Then you can see, okay, you can determine 0 point that now there's no weight on the scale. And if you put load on it, this same bit also responds. So with this, you can monitor is there load on the machine? So for example, maybe the machine is far away. You don't need to go and check if there's a load on it already. If you check this bit, maybe from you are monitoring remotely, the state of this bit tells you there's a load, there's no load on this, on the scale, and then you are sure that there's no load on it. So you can determine 0 points. This is another function, third function. And also, this one is more advanced. It's also possible that besides no weight, you want to specify by yourself a 0 range. So what happens is that for channel 1, this is control register 16. In this control register, you want to set a value, a digital value, that if the sensor is measuring and I read this value, I want to set this value as my 0 range. In real sense, it's not 0, but you are choosing to make it 0. So you have specified it as 0 range. So if you do that, it also operates like this. So what happens is that when the weight measured gets to that point, the bit is also triggered for channel 1. This bit 13 also reacts to it. So if a weight measured is in the specified 0 range, then you can track that, okay, what I'm measuring now is in the range that I specified as 0. That's for that. And then this is the third function. Sometimes you may not need this function if your application is not very sensitive. If it's just a simple application, you don't need all this. But there are some very advanced, you want to monitor every step of the weighing. Then we provide this function to help you to actualize that. The fourth function that we offer in this module is filter out weights. Sometimes when you are measuring weights, the weight you are measuring is being distorted. Like one of our colleagues on the call asked, can you connect a load cell together? Then you connect it to the module. It's like your average what is being measured. So that is being done to measure that what you are measuring is balanced. But in some case, you could have some interference, some noise, the measurement is not stable. Then you can use this function to filter. So everything in the module has an address. So you can access the address from the control register. All you need to do, specify the control register, use to write if the register has a write attribute, or use from to read if the register has only read attribute. So in this function, you can choose the filter mode. You can choose maximum filter mode or average filter mode. So you just like type of filter. So maximum filter mode is like it filters the maximum measurement so that there's no interruption or noise. And the average filter mode, it takes several measurements, and that is approximately maximum of 100 values that's being measured. It gives you an average value. So averaging helps you to have a more balanced measurement. For the maximum filter, you have, if you choose maximum filter, there's a control register. This control register, you can specify the magnitude of the filter. If you choose 8, the filter is so aggressive, so no noise, it doesn't tolerate, it filters it smoothly. If you choose like 1, so the filter is like mild. So this is just like filtering the signal that is being measured. So the bigger the number, the stronger the filter. So if you specify 7 in this register, it means for this sensor I'm measuring channel 1, I'm filtering based on this magnitude. So you can filter out weights on noise weight that you don't want, that your measurement from the sensor is smooth. And then another function again, 0 point tracking. So it's possible once you have made some measurements and you want to go back to 0, all you have to do is just to send command. So then you can reset to 0. So this is, you can also specify 0 range. So that's why this module is very smart. Besides absolute 0, you yourself can choose what you define as 0. I could define 200. For example, I could define 1 kg. If I measure 1 kg on the sensor, and that 1 kg on the sensor give me 1000 digital value, I can choose that this 1 kg for me is the 0 range. So you can specify your zero range, and based on that, you can return to zero from with the control register. If you also go to the command bits, control register 200, here you can send command to return to zero. That's fifth. The sixth function is limit detection for channels. So it's possible that what is being measured, you can save the maximum and minimum value for channels, so peak to peak. So you can recall what was the maximum value that was measured and what was the minimum. For example, maybe you are working on a machine, maybe like a conveyor belt, the weight is there. So every device is passing and the module is measuring different kind of measurements. So you can recall that among all this measurement that was made, what is the maximum value and what was the minimum value? So you have access to that. This is the function limit detection for channel. You can determine the limits. And additionally, it's also possible that when weight measured exceed the maximum weight that can be measured, you have a flag to indicate that the weight I'm measuring is more than what I should measure. So for example, now the sensor I showed to you is 5 kg. If I'm measuring like its maximum is 5 kg and also set it as 5 kg in the module. If I measure 10 kg, so this bit can give an indication that what is being measured is more than. Or for example, your application is filling, it's a filling application, you are filling a bottle or you are filling a package. So if you fill a package more than what is supposed to be there, this bit could trigger that, oh, this sensor is measuring, there's a value that is more than what we want to measure. Then you can take that package out and maybe, and put it out aside and solve the problem. So this helps you to give you a flag if when what is measured is more than the maximum that should be measured. 7 is record for channels. So it's possible to record for like channel 1, you can record everything that is being measured. You are recording, maybe in your machine is working from morning to evening, and a lot of products is going through your weighing application. So you can record what is being measured, maybe 5, a day you want to produce 5 products. So your application is a weight application. The product passing by is like 300 per day, and all are being measured on one sensor, one load set sensor, one channel. So it's possible you can record the input value of the cyclic sampling for each cycle. So this is just a trace. Maybe in the morning I measured, 5 minutes later I measured something different. Then you can have like a trend of what is being measured. For those of you that are used to the HMI, it's like the history buffer. So you buffer what is being measured. So, and for this, you can set the time of record. So the time of record is from 1 milliseconds to maximum 1 second. And you specify the time here. This is for channel 1. You specify the time. At what time do you want to record a data? You want to keep it in the record register. The default is 1 milliseconds, if I'm not mistaken, but the maximum is 1 second. And then also, if you want to see the current record, now a machine, a device or your product is on the machine, on your weighing machine, and you want to see what is the current weight I'm recording now. If this register for channel 1 shows you the current weight, and this register for channel 2 show you the current weight for channel 2. And then the range, so you can record maximum of 500 records. So I believe when 500 record is made, then any new record will be overwritten. So if you need 500, you don't want it to be overwritten. It's good that after a time you retrieve those data, and maybe you want to plot a graph with those data. Otherwise, since it's 500 that can be recorded, if 500 the stack is full, like in the HMI, you can control to stop, you can control to continue, then the stack will be overwritten. Then, so like what was recorded yesterday, you cannot see it today again because new ones fill the memory. That is record for channels. And then there's address where you can see those 500. For Shining One, you have recorded 500 different type of weight that you measured. So where can you find them? From 4,000 to 4,099. That's for Shining One. So if you read this register to your PLC, from this to this, 500 registers, you can get which one. So the record is stamping each register, stamping based on the time you specified. If you specify 1 second, it will take longer time. It will stamp, 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 then you can get them from here. And once you've got them from here, you could do what you want to do with it. Maybe your device is connected to HMI, your weight machine is connected to HMI. The HMI can read the address of the PLC that is reading this, and then you can plot graph with it on your HMI. So what you do with this data is flexible. So, but this helps you to keep track. What have you measured? The load sensor itself, the load cell cannot keep record. It just measure. This weight has come measure. The load cell or the sensor has forgotten, but the module keep track of what has been recorded. So it can record 5 different numbers and keep it in the stack for you. You can use those data to make some analysis, depending on the kind of machine that you have. The last function, before we call it a day, we took quite some time. I was thinking to be shorter than this, is calibration or adjustment of measured weights. So what is the essence of calibration? So calibration makes weight measured by a sensor correspond to the digital value displayed in a load cell module. So what happens is that your load sensor is measuring 1 kg. And that 1 kg can represent, for example, 1,000 digital value, 1,000 in your module. So if you see 1,000, you can tell your module to do what has to be done. So in order for that to be possible, you need to calibrate the module so that if it reads 1 kg, it will give you 1,000. I want to ask the questions. In this case, if I read 2 kg, which value should I have? Can you write it on the chart, please? If I read 2 kg, which value would the load cell module give to me? Just type it in so that I see. Here is 2 kg. What is the equivalent digital value in the load cell module? Good, I can see there's one chart already. Perfect, Shami, thank you so much, 2,000. So for this to be possible, that is why you have calibration. The sensor will only give you a millivoltage, a voltage that is equivalent to the weight applied. But in the load cell module, you cannot read voltage there. You only see numbers. I think I was online in this stuff. You see, I'm still online, probably. Run. Yeah, I think there's distortion. You see, you can see value. So this is the weight, the digital value. So you will not see voltage. So in the module, you only see digital equivalent. So what the module does, it converts the analog signal from the sensor to a number. I can tell my PLC, if you see this number, stop filling the package. If you see this number, stop doing this. So based on this number, you can program the algorithms of your machine. You understand? So it gives you a number. So for you to have a number that corresponds to your read weight from the sensor, that is when you need, that's why when we need these, let's go back again. That's why we need to do this calibration so that we have a correct digital value that is reciprocal or that corresponds to the analog value coming from the load sensor. So you do that with calibration. So there are 2 different types of calibration. The first one is what we call just the real-way calibration. So this is the flow chart of the calibration. How do you do it? First of all, It's possible, you can see here, it's possible to calibrate 20 points. You can see on this picture, this is 1 point, this is 0 point, this is 1 point. So this is 2 point calibration. So it's possible to calibrate 20 points in case there are different, the tolerance of the sensor, yeah, it's not very strong. So what is coming from the sensor is not linear. You can calibrate several points and say, okay, if I have this from this sensor, give me this digital value. So the load cell modules will be giving you value based on what you have calibrated. So it's like a trick, you understand? I can calibrate this as, okay, if I read 1 kg, give me 10,000. It gives me 10,000 because that's my calibration. So this is the order of calibrating. We have a register. You see, for everything, there's a register. For channel 1, the calibration points, I told you 20 points can be calibrated, is control register 18. In this register, if you write 2, it means that you want to calibrate 2 points. That means 0 points when there's no load and 1 point when you have load. And then the weight calibrated, this is very important. This weight calibrator is what you have here. So if I measure 1 kg, what do I want the load cell model to give to me? If I want 1,000, then I write 1,000 in this register. If you see this register is 20, from 19 to 58 for channel 1, or 78 to 119 for channel 2. So if, for example, in 20, if I write a value in 20, it means it's for position 2 that I've calibrated. So the digital value that is there will be what I'll get from the module. So this is how it goes. First of all, you specify the number, how many points you want to calibrate, specify it here. So it's just 1 register, 2 points, you write 2. Then once you have specified the number of points, you go to no weight points. So it's always possible, it's always mandatory to start from 0 to know when you do not have weight. So you specify the no weight point, and then what you do, you calibrate it. To calibrate this register, command set, you write 98. 98 means right adjustment. It means, I showed it to us before, activate calibration. Have you done that? Yes. So you have done 0.1. Do you want to do 0.2? No. Then you write 99, disable calibration. It means you have done 2 points. But do you want to do more points because you want your measurements to be so precise? You want your digital value to be as accurate as much as possible? Yes. Then go back to this stage. Then in this register, then you write 0.3. If you write 3, it means I'm going to number 3. You can also do it in the, this is one way, let me not confuse you, this is one way. So what I've explained is with the control register, you specify the number, then you specify the digital value, you enable calibration, it's like a loop. You continue until the number of points you want to calibrate. That is one. Another way that's possible is this. If you come to like, let's go to the software. That was with control register. You write, we use to and fro. If we come to this place, you see this is a status code, and this is command. This 2007, there is, is state code, a command. The command is 20, control register is 201, but the CPU is giving us this 0. So what happens that you write the command here. This is where you write the command, but there's where you specified which number you are going to, which point are you calibrating. Is in this place. It's from, let me see, status code, command. So what I'm trying to say that when you write it here, like I'm online now, for example, if you write a command on this D0, without using to instruction, it goes to the register you are calibrating. So you can do it from the monitor table, you write that. But with this, you are a little bit limited because you don't have access to a lot of parameters. But with the control register, that was like a little bit more flexible, which I showed to you here. What you do here with control register, you can also do it with the mapped register, which I showed to you in a DI designer. So this is the first option of the calibration, that is function 8. We have seen function 7. The function is function 8, reweight calibration. So you reconcile what you are really weighing to the digital value you want to have in your application. And then number 9, this is the last function, is theoretical calibration. So instead of you putting a reweight on the sensor, you don't do that. Now you already know the specification from the sensor. 1 millivolts, for example, is equivalent to 1000 digital value. Then 10 millivolts. So if the sensor internal circuitry outputs 10 millivolts, it means it's the weight applied on it that produces 10 millivolts. That weight is 10 kg. You can reconcile that. So if I measure that, okay, I need a digital value of 10,000. So this is the flow. And for this theoretical calibration, you don't need to put weight on it. What you're just doing is that in this place where you write this register, where you normally should have written the weight, what you do in that place, you just write the voltage, the millivolt, 1 millivolt. 1.0 means 1 millivolt. 2.0 means 2 millivolts. So you write it. So 2 millivolts, when 2 millivolts is equivalent to the digital value that you have set. So when you do that, you are just using millivolts, not real weight like the first case. It's theoretical, it's not practical. You are just assuming that if I measure this millivolts from the sensor, I want to have this digital value that is being calibrated. I think for this, there should be a control register for the theoretical voltage. But for this register, this is where you specify the digital value that you want. For example, 1000, you write 1000 here because when it measures 1 millivolt, there should be 1000. Also in the load cell module, load cell wizard, you can also do that. So this is the flow. It's just the same like what we saw before. So once you calibrate this, it measures that your sensor, the digital value of your sensor is corresponding to the analog value. Sorry, the digital value of your load cell module is corresponding to the analog signal that your sensor has measured, and then you can play around with it in your application. So this is it. And other thing that is so important is, I told you this before, control register 200, each bit error code is here. And on the manual, you'll find other error code information that could be helpful to your application. Before we take 1 or 2 questions, if we have questions, let me just show you a little bit on the software. So now let's come to the configuration. See configuration. It's already open before, but let me open it again from here. If you click configuration, it opens this. So I'm online. Let me go offline. So now what we're going to do, let's calibrate this step up to calibrate. For example, if you double click on this, it opens the load cell module. Would you like? Yes. Okay. I'm not online, I'm offline. So what happens is that the first thing is that channel 1, here you can select what do you want to display. So this is control register 0, control register. What do you want to display? Is it the gross weight, the net weight, or the tail weight, the raw data? You specify it here. For example, let's specify gross. Gross is everything. And then this characteristics value is the end game value. Like I showed to us earlier, if I come to the presentation, you will see I put a picture. I think it should be possible to see. Yeah, I put a picture of the specification. Sure. Yes, or the specification of the sensor. I think that was when we were looking at wiring. Perfect. You see, this sensor that I have over here, the ion gain value is 1 millivolt. So each sensor have a specified ion gain value. If I switch, let me see. If I switch the camera, you will see it. Yeah, it's just a generic sensor. Yes, you can see. Yeah, this is it. You can see it here. So the characteristic value, the ion gain value of this sensor is 5 kg. Maximum kg you can measure is 5 kg. Is the ion gain value is 1 millivolt. This is what you are seeing on the screen, 1 millivolt. So it's very mandatory. If you want to what this sensor is measuring, if you want it to be correct, if you want the load cell module to have correct value, you have to select 1 as the ion gain value, the rated output in the load cell module. So you can see this is the setup. So let's go back now. We switch back the video, and then let's go and continue. Maybe later I will switch back to the video when we had some load on it. So if I go back, I keep this. If I go back, so you can see where we opened the load cell module was opened, the load cell wizard. So now here we select the ion gain value. The maximum we support is 80. So it means that for this sensor, the maximum, the ion gain value supports is 1 millivolt. So if you want to have correct reading, you must select 1 millivolt. So if you go and select other thing, the reading will not be accurate. So this is very, very, very important. And then the sampling time, this is the time it takes for the time it will take for the load cell module, to sample the analog signal coming from the sensor. So what the sensor is giving to you, how long will it take it to read it? So you specify it. So it's advisable, if possible, if your application permits, set bigger time as much as possible. You can see that the default is 50 milliseconds. It's at the middle. If you set bigger ones, then the module has enough time to sample the sensor data and give you a steady and stable value. And then you see these are other functions, stand still. You see maximum weight. The maximum weight, this is like the maximum digital value that you can set. So 100,000, you understand? So if you set this maximum, it means when the sensor measures maximum, the maximum you have set is the digital value. So the maximum digital value that of the signal coming from the sensor is quite tricky, but I think you got it. So this is it. So for the digital value, you can say the maximum is 1,000. So this is the default. I don't know if you can go beyond that. You can even go beyond that, but the default is 100,000. So I can say 100,000, 10 kg, for example. It means if my sensor is measuring 10 kg, the module will give me 100,000. So then let's continue. So I'll select 1 as the ion gain value. We want to measure gross weight. So this is the main first configuration you have done. So let's download. So you download. You see download sources. I've downloaded to the module. Then let's go online. So you see I'm online. This is the value I'm seeing. So I'm seeing this value is from the sensor. Okay. Then how do we calibrate? So calibrate, you just go to calibration. Let's say monitoring. Yeah, I have some error. That's what you CPU you can also see it. Input is out of measure range or sense voltage error. Maybe it could be the sense voltage cable is not well connected. So this monitor gives you what is probably happening. And then let's calibrate. So the step to calibrate is this. I'm online. If you click start calibration, so you say wizard, it just take you through the process. It's quite easy. This is the first step. So the minimum step you can calibrate is 2. You cannot calibrate less than 2. And then how does it go? This is 0.1. That is 0. It means there's no load on the sensor as it is now. There's no load. And then let's proceed. If I click next, the user will ask you, make sure no load is added. That is true. There's no load added. So now it's stable. You can see that the value has gone to very 0 level. Now this is 0.2, calibration 0.2. So if now what happens in this case, I should put a real weight on the sensor. Let me switch the video. So the essence of this is that what the sensor measures, it will give you a correct digital value that you can use in your machine. I switch the video to the module, but I have some error. I think if the error is not cleared, everything may not be perfectly okay. But this is just the principle of how it works. So now you can see the sensor is on the ground there. So the sensor is on the ground. You can spotlight the video in the recording so that it's big. You can see the sensor now, there's no load. Then what happens is that if I put a load on the sensor, what should be the digital equivalent of this load? Assuming this load, for example, is 1 kg, but I measure this load in the office, this load in a different scale, this load is 0.8. It's not up to 1 kg. So let me try to position it on it. Yeah, we are still getting some reading. So what happens is that it will soon, just a moment, sorry, it's a stand. Okay, I leave it like this. There's some weight on it. So what is happening now is that if I measure this, what is the digital equivalent value I want the sensors to give to me that for this weight I'm measuring, assuming it's 1 kg, for example, then I should have 1,000. So if I click next, make sure the standard weight are added. Okay, I hope you can see the sensor now is hidden because I've put a weight on it. I click OK. So you see now, you see what I can see. You can see 1,000 here. It means that for what I'm measuring now, the digital equivalent is 1,000. If I apply more, so let's finish the calibration. Finish. Okay. So basically, this is how you calibrate. So you calibrate that the weight you have measured is the equivalent, the digital value is equivalent to what you are being read. So like in your application, so you can play with, you can use any value to represent, you can use values to represent what should be the digital value you should have for that very weight you have measured. Yeah, so I think for the practical session, we'll not go so deep. I will stop the practical session here. So if you have any question, maybe that's related to what you have done so far, you can ask. I also have my colleague is on the call here to support us with your application question. Maybe I facing some issues, so you can ask, and then we'll trash it together. Come to monitor. Okay. I will now switch over the video. So that's how you calibrate. So once you have calibrate, then you now have a digital value that is corresponding to the analog value coming from your sensor. So this wizard helps you. And besides this wizard, like we already seen, you can use a to from register to calibrate. All you just have to do is to write command, and you also do the same thing. So they specify the digital value, and then you are ready to program your machine. So do we have any question? If you have any question, you can type it on the chat. Then we can discuss it together. Maybe in your application before you face some issues, or there are some things you want more clarification, and then we can like trash it out together. So this is the load cell module. Mind you, I use GL Designer. For those of you also that is familiar with ISP Soft, you can also use ISP Soft. So when you open this load cell with an ISP Soft, the procedure is the same. You calibrate with the wizard, or you calibrate using control register. So, okay, if we don't have question, I will just see if my colleague David has some remark on what we have done so far, or general advice, so you could give to us, then we can close this meeting. And please, I beg your indulgence, once this meeting is ended, a survey will pop up. Please, it's just like 2 minutes or 1 minute. Please just fill the survey. It will help us to improve on the training. Prior to this time of pandemic, we don't have online trainings. It's the pandemic started. Now online training is not like the core in most places. So, David, are you there?
Yes, I'm there.
Yeah, could you just give a general remark or advice application-wise? Because some people here, they are machine makers, like Shami, he has worked with load cell before. Just general remark on what we have done. Then we can close the meeting, if any.
We don't have any comment. If none of the others have any questions, I think you did a good training, and it was complete and tackled everything. So yeah, I think, yeah, from my side, there's nothing to add.
Yeah, okay. Thank you, David Gomze, alumni, Alfred, Ecotech, Jeremy, Tosca, and Shami. Thank you all for your patience. The meeting will end now. David, also thank you for coming, for leaving your busy schedule to support us. We so much appreciate you. We'll end the meeting now, and you'll get the survey, and please just fill the survey to help us. Thank you, everyone. The training has ended.